Welcome all. This is, as I'm sure you're aware, this is one of the CCOM Masters defenses that we host quite regularly. There was one just a couple of weeks ago, and there's some coming up in the next few weeks. We'll follow the usual procedure. The committee here, myself, John Hughes Clark, you see Brian Calder and Tom Weber, but Lieutenant Commander Ivan Bodra Guimaraes is defending today. He's an officer in the Brazilian Navy, the hydrographic branch. He's been doing offshore, coastal and river surveys for the last decade, and he actually forms part of a long line of really professional people we've been lucky enough to have both here and actually back at UMB as well, who've come through our programs and both worked with us but also brought an awful lot of experience because, as I mentioned, they're all professional surveyors. And Ivan, today, this is the culmination of 24 months, very strict 24 months that not all other graduate students achieve. He will be in uniform at the end of this month, and he'll be defending today his thesis, Calibrating Multibeam Backscatter. I believe that's the title, but we'll see. So rather than delay anymore, Ivan, if you care to share your screen. Oh, actually, while you're doing that, I'll mention the procedure. He'll be talking 30, 40 minutes, something like that. Then we'll have a round of questions with the committee, the three of us. We might go around a couple of times. I then open the question to the group here. If you're interested in asking a question, just queue it up in the question and answers. We'll be looking at them, and well, you can turn on your mic and you can ask the question, or we can read it out as well. But that's the usual procedure here. So go ahead, Ivan.
I hope you can see my screen now. Okay, well, good afternoon, everyone. Thank you for all of you that are here. I may be a little nervous today. It's a very important day, but I hope I can deliver a good presentation since the project is very important. It's not only made by me, it's a long process, and we will see that it has a lot of history on it. And I hope you can enjoy the presentation. So the project we've been working on is the Calibrating Broadband Multibeam Seabed Backscatter. And to make a comparison with, whereas we have the bathymetric calibration, then we know how deep the depth of the place and how accurate that measurement is. And we also have patch tests and all sort of improvements to that measurement. In comparison to the backscatter calibration, which is the intensity of the same signal that provides us the bathymetry, we don't have a value associated to it. We just know if it's more intense here or less intense there. It's just relative. It is, if we compare, it would be if we said, oh, this is deeper here and shallower in that place. And of course, for bathymetry, we need more than that. And for calibration, as we will see, we want to get better in this level of intensity here. So if I can click to the next slide. Okay, good. So the National Mapping Program from the Irish government, which is a reliable institution, they provide in publicly the bathymetry of their surveys, and also they provide the backscatter mosaics. And if you take a look closer to those mosaics, we can see that there are some unrealistic boundaries along these lines due to different echo sonars parameters, due to different systems, or even the same system in different times, different pulse length or other parameters. So, and that makes uncomparable adjacent regions that are uncomparable to each other because of this lack of calibration on the backscatter. So in the United States, bringing to the United States, the need for calibration is, in last year, we just had a presidential memorandum that let's add to characterize the US economic zone, among other features that they want about the economic zone. But characterizing is one important here. And if we want to use multiple year surveys, multiple ships, and multiple sensors, and want to compare each other, then we need to calibrate the systems for backscatter. So let's take a look at the Multibeam systems that we have for a reasonable long time right now. So we have these Multibeam systems that have multiple sectors, maybe dual swath as well, and we have each sector works in a different frequency, and each sector will produce a different beam pattern for each sector. And if you take a look on the left-hand side of the figure here, we can see in the boundary a difference in the pulse length that would make a difference in the intensity of the backscatter. Of the backscatter. And once the ship is rolling, we can see the wiggle effect here in the boundaries of the sectors. Well, for visualization, we have the standard of normalizing the response. So this is the Guimaraes angle, the angular response curve that most of us are used to see. So we have the backscatter response and the angular and the angular domain here, and we just normalize it to a level that makes the mosaic smoother, and then we can see the boundaries of the actual geological features. However, we still have some, depending on the sediment that may be softer, we still have this feature that is not related to any geological factor. It's just the angular response curve that has a stronger specular response near normal incidence. And we want here to make use of these curves that makes the signature of that sediment type. Is the reason for visualization here in this project is actually not that important, but the use of these angular response curves are important here. So, well, calibration is not unusual in other industries. Let's say fisheries, they need to know the amount of fishes they have underneath their transducers or the size of the fish, and to do so, they need to calibrate their system. But they use a different system that are the split beam that works as a single beam with different receivers. So in the project here is 4 receivers that we can split in 4 different quadrants. And if we compare 2 pairs of these receivers, we've compared the difference of phase that we receive the target, then we can locate in a cross track, and we select the other 2 pairs and a long track angle, and then we locate any target within that, and then we can acquire the target strength as well. So if we swing by a sphere, and that's how the procedure of the fisheries calibration works. So we swing a sphere with a known target strength there. So it's a tungsten calibrated in this case. There are different diameters that make a different target strength response. And we know that the model here is in the blue line. So this is the frequency domain. It varies with the frequency. And the difference that we acquire from the sphere with the transducer to the model is the calibration to that transceiver. And since we are swinging by the sphere along underneath the system, so we know where is the maximum response axis and where it reaches the different level that is 3 dB less than the maximum response axis. And if you take a look on the frequency response, we know that for higher frequency, we have a narrower beam width, and for lower frequency, we have a wider beam width. Well, let's take a look at how would it work in a multi-beam calibration. If we did the same procedure, well, the first thing we will notice is that we have very narrow beam width. It's not as large, not as wide as the split beam that has 5-7 degrees of beam width, and here we just have 1 or half degree, depending on the system. So swinging bias here would have to be very accurate there to get each one of these receivers. And of course, we have multiple receivers. We have more than 200 receivers that we need to calibrate each one of them. And so how would you get that far to the sides of the ship? So that would be very difficult, very hard to achieve in the multi-beam calibration on a ship. Other than that, we don't have a long track resolution for multi-beam systems, not so far. So we need to get around this, and the way to do so, we can point that to the seabed. So we make use of the seabed, and you constrict that grazing angle, that angular response curve with backscatter with that split beam that is calibrated. So we mount the split beam on the plate, we rotate the plate on the seafloor, and we have the actual response of that seafloor. With that, we can use the multi-beam system over the same seafloor and check what are the answers that we have. So we can compare for each sector, near nadir and both the other two on the sides, and we can compare the angular response curves, and that would be the calibration for that multi-beam system. So by using the reference, we can calibrate the multi-beam system. That's the concept of this project. It's not a completely new idea. We've been working through other projects. It's an ongoing program that is not like we can relate to other projects here to get this idea. And what we have, so in 1954, we already have Yuri keep developing this plate that can mechanically rotate to get the angular response curve. And this is the angular response curve that we can get from CW pulse. And if you take a look at a 3D model of these, saying this is the axis for the grazing angle, this is the axis for the frequency, and the backscatter strength. So the BS backscatter strength response in decibels here. So that would be the response for one pulse. Well, he did multiple pulses. So he had to swing to rotate that plate for each CW pulse, and then again and again and again. So he could build several curves in this lower range of the frequency range. So, and he could note that might have some frequency dependency on this angular response curves. Well, in 2015, Weber and Ward did a very important achievement for these projects here for the need for the calibration, and which was they were pointing at 45 degrees. So it's just one point in this angular response curve, but they used an FM pulse. So by using the FM pulse, chirping from 160 kilohertz and 260 kilohertz, we could see the frequency dependency of this response, which was very important. And in 2018, Ifreme make the comparison between the split beams and the multi-beam systems. So they used CW pulse, not FM. So CW pulse in 200 kilohertz and at 333 kilohertz. And they had, by rotating and pointing on the seafloor, they had the reference. They built the reference with those systems, the split beam systems, and they used in the black line here the multi-beam system to compare with the reference, and that difference would be the calibration for the multi-beam system. So they used the EM 2040, the multi-beam system that they use, and they acknowledged that because of the sectors, and they were assuming that, oh, okay, we are using CW pulse and maybe it's enough for the whole range of frequency for the sectors that use centered in 300 kilohertz. However, they noticed that there was some divergence on the response that might have been due to the factor of the frequency dependency, that the they didn't accounted for in these projects here. So we want to make use of all these projects that came before us. And since we are, I'm from the Brazilian Navy, and looking towards the other main institutions, so in Canada and NOAA and Naval as well. So we all have in common the systems EM710 and EM2040, which covers the range of from 45 kilohertz up to 400 kilohertz. So that's the frequency, that's the range of frequency that we are talking about. And this method, there's no reason why it should not be applicable to other systems that use the same frequency range. So the equipment that we are using to make the reference are split beams, 4 transducers, ES70, ES120, ES200, and ES333. We mounted those, each one of these transducers on the same plate that covers, using FM pulse, the whole range of frequency that we need. And then by using that plate and rotating that on the sea floor, we could, using the whole grazing angle, so all the angular response curve can be built here. So that's the concept. So to choose areas, we made use of the Canadian Hydrographic Service data that was available to us. And by analyzing the data, we could see that we had 5 very important areas that had important features for us that was beneficial for this project. And we have selected on the west coast of British Columbia in Canada areas that vary in depth between 10 meters and 55 meters. And what that represents is that in 10 meters, we would cover, by rotating up to 80 degrees, we would cover an area that is 100 meters wide. So we are using the ship anchored and rotating that plate, and then we need this area to be covered. And at 55 meters deep, it would be 550 meters wide. And what that represents is that we need that whole area to be homogeneous. Since we are using that as a reference, we need that to be the same type of seafloor around this whole area. And we select different regions here with different sediments: mud, sand, muddy sand, shell hash, and cobbles. However, it's not important to know which type of seafloor it is on the method. It was useful to make some evaluation of the data, but in practice, we don't even need to know, as long as it is the same type of seafloor over the same area. So we collect the data, and I'm going to work through each one of these steps here in the data workflow. And there's one point that's important. We are going to go through from the time domain, applying Fourier transformations, to go to the frequency domain, since we have some variables that are frequency dependent. So one equipment that we had in our favor was the MRU-6, which is a motion sensor that provided pitch, heading, and roll. And with that, we'd know the attitude of the plate. So we use this match filter, which is convoluting the received signal with the transmitted signal to get the echo envelope. So with this match filter signal, we have still preserved the frequency the frequency information of the signal received here. And we are going to make use of the across and along track, mainly the across track, since we're talking about the seafloor, so which is the phase range. So for the bottom detection, 2 weeks ago, we had Leonardo presenting his defense, and he talked in very good detail about bottom detection. Here we are using just the simple part of it. We just need to locate the target in the case of the bottom. So we can make use of the amplitude detection, whenever we don't have the phase, the zero crossing, so near nadir, near normal instance, we just need to rely on the amplitude detection. And when we have phase information, we can look for the zero crossing and make that our bottom detection. And around there, we extract the data that we need. So what is the grazing angle? The grazing angle that I've been talking about is, if we assume a flat seafloor and a straight beam without bending, that's the grazing angle that can be related to the pitch and roll, assuming the MRU is well aligned with the plate. So with the pitch and roll, we get the grazing angle. However, the seafloor is not as flat as we assume. So there is some relief, and of course there is some ray tracing. So the grazing angle cannot be actually related to the pitch and roll, and we need to make use of the phase ramp, and we'll see how it works. But first, I just want to mention that near nadir, where we didn't have the phase ramp, enough phase information, we don't have a lot of effect from the ray tracing, whereas for lower incidence, for a lower grazing angle, we have stronger influence of the ray trace, but we have a neater phase ramp here. And from the phase ramp, we have the information that we need to build the triangle here that we can solve. So we have the range that are the size of the triangle and the angle between the 2 points on the phase ramp that make the triangle, and then we can infer based on some geometry here, we can infer which is the grazing angle. So with that, we don't need to calculate any retracing. Actually, we just use the phase ramp, and by using that, we have the grazing angle. So if we take a look of the one ping, and we use just one information of that for each ping, and we assume that it is flat and all the information of this ping is here. However, if we divide the ping in subsets and use the method of high definition, and we are able to, in one ping, define the relief of the seafloor. So from looking at the MRA, so the maximum response angle, where we have the zero crossing here, then we have one grazing angle in that angular response curve. It's just 1 point here, and you can use the whole phase ramp divided in subsets and have multiple points from just one ping. Well, now we want to understand how can we divide this? How fine can we divide this? So this is a matter of resolution, and we are going to talk about this FFT, the frequency, the fast Fourier transformation here. So we are going to go from time to frequency, and once you are using the whole match filter signal, so we have the echo envelope here, and we make use of the whole, not dividing into subsets, just to use the whole ping. We have in the frequency domain a very high resolution in frequency. That's the blue line here. So if you want to have a good frequency resolution, we use the whole ping. But if you want to have a fine resolution in the grazing angle, in the relief of the terrain, then we shorten the extract of the match filter, which would give us a lower resolution frequency. So it's a matter of do I need grazing angle resolution, or do I need frequency resolution? So in this thesis, it's open to discussion, but in this thesis, we selected 64 counts. That's the number that we finally got, which would represent in the frequency resolution about 4 kilohertz. That should be good enough here. So by applying the FFT that I mentioned, so we have the match filter in the red line, which is the time domain, and then we're going into the frequency domain here. So by selecting this subset, we have this frequency response here. And of course, we can make use of multiple, the high definition, have multiple responses in the frequency for just one thing, which is good for averaging statistically the signal here. So now we need to apply all the corrections that we made, that we obtained from the calibration. And the first one is the beam pattern. So you may have noted some bending here, and I'm trying to point it out for you, but well, I'm seeing this data for a long time, so I may see a lot of things, right? But this is before applying any beam pattern correction, and after we apply, it flattens the curve, so it corrects for this lower and higher frequency beam patterns. And also from the calibration, we have the difference between the target sphere and the response that we actually had from the transducers. But in the calibration, we made use of a very high defined frequency response. So that's the difference that should be applied. And since we are using just 64 counts, we don't sample the calibration into 64 counts resolution. So that's what we apply from the calibration. And we also apply correction for the transmission loss due to absorption, which is stronger in a high frequency and is less strong for lower frequency. And also we are insonifying the seafloor, then we want to normalize by the area. And the backscatter normalized by the area near nadir would respect to the beam width limit that is represented here. And when we have some lower inclination, we have lower grazing angle, have more inclination, as a matter of fact, well, then we sweep to a different area insonified area formula. So then we make it pulse length limited. So instead of beam width limited, it's now pulse length limited, sorry. And this tau that we presented, the pulse length, is very used to CW pulses, that is just the pulse length actually. But here we are using FM pulse and match filter signal. So just this tau, this pulse length is just the 64 counts, that magical number that we selected. That's the length of the pulse in commas here. So then we also want to acknowledge that for lower frequency, you have a wider insonified area. And here we can see the frequency and grazing angle. That's the area correction. And we can see the slope here varying from the beam width limited to the pulse length limited. So let's see the results we have. So this is the model. Remember, frequency, grazing angle, and backscatter strength. So before any correction, we have these four transducers, four different transducers, independent, and they have, if you see the response that we have from the seafloor, they are completely uncorrelated. We have steps, they have some weird shapes, features. And after we apply all those corrections and all those considerations about transmission loss and insonified area, that's the response that we have. So they are completely independent, each one of the transducers. And now we can see they are way more related to each other. And that's the reference that we built. So that's for all the 5 areas that we went. So for the muddy sand, shell hash, cobbles, sand, and mud. And if you take a look here at muddy sand, for example, we have a higher specular response near nadir. So near nadir is closer to the wall here, right? It's 90 degrees near nadir. So this is a higher specular response and decays a lot and has a very low response in lower incidence. In comparison to the cobbles that doesn't have this higher response near nadir, it decays smoothly, but it is all the way stronger than the muddy sand. So that's the comparison, that's the results. So that the thesis would end here. So that's to build the reference, and from that we would be able to calibrate our systems. So that's not just stop right here. I want to make some evaluations of the quality of what we had here and some considerations that might be interesting. However, this is the deliverable of the project. So to evaluate, we want to make sure we are talking about the angular response curves. So this is the angular response curve for the frequency at 71 kilohertz. We can see here this of those 5 different areas, and we make it for different frequencies have different grazing angle. So we can see how it changes, and of course it's hard to have any information from that. So let's select just 4 of them, and we are comparing in this case here just the sandy and mud sand. And if you look just for the look, it's hard to tell them apart. We need to measure some grain sizes and other features of them. But in the frequency response, actually in the angular response curve, for the frequency at 71, we can see that those two, the sand and the mud sand, are far apart near nadir, and they get closer in the lower grazing angle. Whereas for 123 kilohertz, they are closer. They are not that far near nadir, and they get far apart in intensity when we get lower grazing angle. In comparison to the 200 kilohertz, where we have a cross from the muddy sand that starts stronger and decays more than the sand. So here it would be great to tell them apart. And for the 333, they are just parallel with difference in intensity. It was interesting. It also you can make it the same comparison between the cobbles and shell hash. You can see they are far apart for lower frequency, starting to get closer at 150, even closer at 293 kilohertz. And you may have noted that we have these weird shapes going backwards. So again, so this is the angular response curve near nadir here, and we don't expect the angular response curve to rise after lower grazing angle. And it's not actually physical expected, and that's probably due to the fact that they are too far apart at 45 meters and 55 meters of depth, so the range is even greater, and it's probably that the lack of any signal to noise response, noise ratio. That's probably the case here. So I'll just go back just to make the point here. So the point is that we want to get closer to the seafloor for these to avoid it. So let's take a look at the other axis now. So let's take a look at the frequency trend, and for each one of this grazing angle, we have different frequency response, and of course going to bring those two to compare. So at 75 degrees on the left and 35 degrees, a lower grazing angle on the right side, we can make comparisons for each one of those areas. So for the muds, in both areas we have the response decreasing with frequency. So we have the frequency domain here, and the response is decreasing in both cases. However, for the sands, we have the response decreasing with frequency for higher grazing angle, whereas it is increasing for lower grazing angle. And for gravels, it's variable for higher grazing angles, and it's decreasing with lower grazing angles. So by being that long time looking at those data, we start to notice some features here that, if you can see, they are in 5 different areas, so they shouldn't be completely independent, but we start to see some similarities in shapes of the response, and we want to make some investigation about it. So we can see there are systematic features here. And so let's take a look at how different they are from this trend. This trend here, the red line, is a 3rd-degree polynomial that we may use of this frequency response to infer. And if we compare the actual response to this trend, then we have the next plot. For each sector here, for each 5 degrees that we are going through here. So that's the difference. We can see that the difference between the trend, between the frequency response to the trend, is less than 3 decibels, and most of the time the RMS is less than 1 decibel. It's not that much, but it's systematic. So if you sweep by again, we can see sometimes it gets closer, and I want to make the point here. So I select just the grazing angle from 41 degrees and 70 degrees. So the grazing angle from 41 and 70 degrees. And that's the angular response, and that's the frequency response of this. We can see that there is a systematic response here. And for each transducer, we can see, I'm pointing out here just to show that near the edges of each frequency range of each transducer, we have higher variation, whereas within the most of the frequency range, the variation is closer to 0. And for the mud site that is 55 meters deep, we can see that the variation is stronger. So let's take a look if we can find where it comes from. We look at it from the sphere calibration. So this is the plot for the sphere calibration. If you remember, you had a high resolution response for the frequency calibration, and then we had the response downsampled. And if you trace a trend to the same line from the calibration and make the difference for each one of the transducers here, so we have the 4 transducers here, then we have the difference within the same margin between -3 and 3 decibels, and most of the case RMS less than 1 decibel. And if you plot against this calibration effect to the bottom response, I might be biased here, but I think it is strongly correlated, but it's not completely correlated. It's not 100%. There's something else that is contributing, but the investigation stopped here. That might give us some confidence about the method. So to summarize what we've been doing here, we calibrated first DK sonars with a well-known target sphere procedure. And then we used the FM tools to get wide range of frequencies with 4 transducers. And then we put the transducers on a plate and rotate to get all the grazing angles on the seafloor. And with that, we build the references for each area that we can use just one area. It shouldn't need 5, but with that, we build the reference. And that's the project. And with this reference, the next steps would be to cross-calibrate multibeam systems at the same seafloor. We go on the same seafloor, you sweep with your multibeam systems, you compare each one of the frequency. You don't have to use just the closest one. You have more than frequencies in that reference. And of course, you can calibrate other ships and other systems with all the whole range of frequency that we have available. So at this point, I'd just like to acknowledge Kongsberg for lending the equipment and providing a lot of insightful questions and answers. And for the Brazilian Navy for the opportunity, and my advisors for being so important here, so orientative, and for my family and everybody. So should you have any questions, I'd be more than happy to try to address them. So thank you all.
Thank you very much, Ivan. I'm never quite sure how we can show our appreciation. A standard talk, we'd all clap now, but with defenses, it's debatable whether it's now or after the discussion. But, appreciate that. So as I mentioned, what we'd like to do at this point is go through the committee twice probably, and look at some of the issues that we've identified. Obviously, we've all read the thesis, and so that we can sort of look at various aspects of this. So as I'm the supervisor, I'll stand back. If Brian or Tom, Brian, your video's up now, if you'd care to have some questions for this.
Sure. Yeah. Thank you, and thank you, Ivan. That was very good. I'd like to go just to that last point that you made when you're summing up there, and I recognise that it's the further work piece that you're recommending we do, but you talked about the difficulties in the response curves that you saw, which were focused on where the edges between the different transducers that you had to use to get the frequency range that you wanted. Yeah, just right here. So the conclusion to this seems to be, from what's in the thesis at least, that the issue may have been the calibration, sphere calibration part that didn't work out so terribly well. Now, it's a delicate measurement, so that's maybe not unexpected, but what do you think happened? What do you think the physical cause for these issues are?
So, well, yeah, so from the response from the calibration, we can see, I didn't bring it on the presentation here, of course, but we can see that on the edges of the frequency range, the signal drops very strongly. So to compare that with the sphere model, it is hardly achievable. It's probably you probably need to shrink to narrow down the actual frequency range that the transducers are using. So instead of using the whole frequency range of the transducer, so let's say the AS70 that goes from 45 to 95 kilohertz, you just shrink that from 50 to maybe 90 kilohertz. Then you avoid this drop off on the edge of the frequency.
Okay, and so you would then interpolate between to give you the rest of the information. So you just focus on the center frequency ranges and then interpolate the rest of the curve. Is that the plan?
Yes, I believe so. So because when we compare with the sphere, so there are some nodes of the sphere that we don't. So there are some already interpolations in the frequency range that we need to make some considerations to disregard this response, because there is some strong drops where so what happens is that we have the frequency, we have the pulse signal going to the sphere, and depending on the frequency of this pulse, it goes around the sphere, and we have some physical interference that goes back and have no signal, and that then we don't use this frequency response, this narrow drop off. So I think it would be the same case. So in the edge, we just interpolate to the next transducer.
Okay, and so the other issue that you highlighted was that the performance of the 300 kilohertz, the 333, was significantly poorer than the rest, or the calibration was significantly poorer than the rest. Is that just connected to the same thing, do you think, or is there something else going on there?
I think it's exactly the same thing. It's just worse because on that range of frequency there are more nodes, and the response of this model sphere at that we selected, we have greater slopes and more nodes within that range of frequency. So we need to interpolate more, and we needed to have some considerations about the slope that we didn't So if we select a different, maybe a different diameter of a sphere of a different diameter, then we would avoid that amount of noisy, if you want to say that.
Okay, so some better experimental technique might solve some of these issues for you. They're not physical fundamental issues. They're just something that could be resolved with slightly better setup, maybe.
Yes, yes.
Good. All right, just to remind everybody before I pass the questioning on, for those who are in here as attendees, there are now 61 of you. If you're thinking of questions you want to ask, now would be a good time to put them into the Q&A so that we can go and read them out, or to nominate you to read them out yourself. We can turn on your microphones as well if you want to. Or if you really want to, you can raise your hand and we'll get to you that way too. All right, I'm going to pass the questioning on to Tom, I think.
Okay, I think I've just unmuted myself. So Ivan, thanks. I think it's a great presentation and a really nice piece of work. And I think that it's a great step forward for calibrating multibeam. So thank you for undertaking this effort and for sharing that with us. I'd like to pick up kind of on exactly the same things that Brian was just talking about. First, just a comment, and that is that we probably wouldn't use a 38.1 millimeter sphere for the 333 for the reason I think that you know as well as anybody actually is. It's just looking at the frequency response. It's a tough one to try to use. But I'd like to talk about you know, some of the things that you identified that really, particularly that ripple that you're talking about. And my first question is, as you did these calibrations, the system that you're using has a way to view, you know, they have a calibration tool that you can run while you're collecting the data. And it shows you the frequency response of the spheres. And were you running that when you did this calibration? Maybe it was too long ago. That's okay if it was.
No, I mean, I can have the expected response for the target sphere, right? And of course, in the EK80 software,
yep.
Then we have the model. Yeah, we use the EK80 to acquire the data, and we process it in a different software. But yes, we use this visualization. Yes, it was very helpful actually. Yeah.
Yeah, no, it's definitely helpful. And I guess the reason that I'm bringing that up is that, well, that's the only way you can collect EK80 data. So I'm sure you use that. But when you're doing that calibration, they show you the frequency response. They show you both a model for the frequency response. You have to put in what sphere you're using, what size it is. I think you have to put in the temperature and things like that, which has an effect on the response. But then they show you both the model and they show you the data that they're collecting. So they actually you give it a window around the target and they show you their version, their processing of the sphere. I'm just curious, there's no right or wrong answer here. Were you looking at that when you did this? Do you remember what that picture looked like? And the reason I'm asking is that if you look at their calibration thing, I don't think they have any of that ripple in there. And that's for the data, not for the model. It's for the data. And they don't have that ripple in there. Do you remember seeing that?
Well, I remember seeing, yes, and I made a lot of comparisons trying to get there. And but the thing is, their response was very smooth.
Yeah.
And I would assume they made, no, I wasn't supposed to assume anything, but I got to the point that I thought they might have been using some curve fitting to get the response, because what I had when I saw the raw data, even before any comparison, is because I had these ripples there. So yes. The ripples were there.
Yeah, so I think that, so this is something that I've looked at a bunch, particularly this summer, and it's a shame we didn't get a chance to chat about it. I actually was talking with the manufacturer about this summer too, because I kind of got confused a little bit in looking at this. But when when we have done in the past these calibrations, we see exactly the same ripple that you're talking about, and it's always been there. And then that, you know, when you do those calibrations, you're using the sphere as an absolute reference, and you're looking at the difference between what you got and the model, and that difference then becomes your calibration factor. And in the past, what we've said is, okay, well, that ripple is just there in our calibration factor, and we apply it directly to the data. I think that when I looked at, well, I guess I think in your thesis, you go into that in a little bit more detail. And I feel like, and this, I guess this is my question, when you did your calibration, did you then, before you applied your calibration to the data, did you smooth out the ripple with some curve fitting or smoothing thing in frequency space? Or did you leave the ripple in there and then apply that just ripple and all directly to the data? Do you remember which one you did?
Yes, I remember. And what we did was, we have this high definition resolution in the frequency for the calibration. But since we chose to select just 64 samples for the FFT, then we had to downsample the response for the calibration, which eventually got rid of the ripples. And if we take a look at this response, so in the gray line was the calibration result, and the blue line is what was actually applied to the bottom. So we don't, by downsample we have less ripple. If we say it's not as smooth as using a curve fitting, but it's less than the actual the high definition. Of course, if we select a longer extract of the match filter to apply the FFT, instead of 64 counts, if we select 200 counts, then we would have more ripples than we had, even more. Yes.
I'm not sure that actually removes the ripple as much as it just makes it difficult to see the ripple. But if you note that your blue points are hitting are smack on top of where the gray curve is, perhaps. I'm not exactly sure what you did there, but here's another question. When you just looked at it, when you're doing this, you do the match filter. Did you look at the frequency response of just the match filter by itself? Just the ideal match filter for the, I mean, the signal, the filter you're actually using, the ideal replica is what I'm trying to say, but not saying it well.
Well, I'm not sure which part. So would you rephrase that apart? Which part of the match filter that you want of the FFT?
Yeah. So when you do your match filter operation, and I believe you did do a match filter on these data, you basically create an ideal replica, right? And then you correlating that essentially with your data. Did you, when you look at that ideal replica, so the signal that's created that, is just, it's your theoretical signal, it's not your data, but it's the one you're using as your replica in your match filter. Did you look at the frequency response of just the ideal replica by itself?
So actually I had to use that because I normalized it by the autocorrelated function in the frequency domain. So yes, I had to make the frequency response of the transmitted signal, the ideal transmitted signal that I use for the match filter.
So this is the part where I'm confused, because I think that if you go and properly normalize by the frequency response of your replica, you can get that ripple to go away. I think it's a Gibbs phenomena thing. It has to do with the shape of the envelope of the pulse you're sending. You're using, in the EK80 vernacular, I think you're using fast ramping. So it's a bit, not perfectly sharp, but a bit of a sharp corner. And I think that I suspect that the ripple is coming from there. And when I think what the manufacturer does is that they go and they basically look at they take the data, the sphere response, in this case, the data, and they they divide by the magnitude or the absolute value of the autocorrelation of the replica, its frequency response. They divide by that. And I've done that on the sphere data, and I've looked before and after, and it does actually make the ripple go away. And you do end up with, you know, that very pretty looking curve that is in there in the EK80 software when you're running the calibration thing. It's not a difficult thing to do. And I think there's a bit of a philosophical difference between, it probably makes sense to do because it's nice to remove ripple if you can remove ripple, but you either need to remove it in both places, both in your calibration data and in your actual data, or not remove it in either place. And I wonder if what's happened is that somewhere in your processing, you removed it from one, but then didn't remove it from the other, or vice versa. And that's why the ripple has remained in your data. I think this is a pretty straightforward thing actually to go and remove straight out of your data. So I think that's the good news. I think it's something we can chat about if you like, and get this straight out of your data. And I think it'll make your result look a lot nicer.
Well, thank you. It was very important. Yes, I noticed the ripples on the FFT of the autocorrelated function.
Yeah.
And I think we may have some heading there actually. Maybe I didn't apply that properly in the calibration, and when I applied to the bottom again, we got the ripple again. So
yeah, if you're like me, the first 4 times you did it, it did not work properly because I made a mistake. It always takes 5 times. I don't know why. I might
need to make a couple more mistakes then no, right. For sure.
You might have more in the queue. Okay, so that was a good one. Do you want to kind of rotate through everybody, John, or how would you like to do this?
Yeah, I think let's cycle around, just have a different sort of speaker. And I think this is all very valuable. It's the method I think we're all very keen on, because as Ivan pointed out with this, the NOMEC, the characterization coming up, we want to tune this. And often, and I think actually Lars is on the line, it's always nice, so we're trying to replicate what's inside the available software already, but it's an academic exercise to make sure we're reproducing and understanding.
He's a very helpful guy to talk to, by the way, when you have these questions. It's super helpful. Yeah.
He should, yeah. I'd like to, Ivan, look at something a little bit different here, and that's more the geometrical one. Could you just flash up the 5 results, which I find exciting from a geological point of view?
Yeah,
there's another quiver in there that worries me. Remember which slide it is.
I think it's 36 if I can get, I have this. Is that this one?
Nothing's changed yet. There we go, yeah. I mean, you see this lovely angular response. You'll notice in almost everything, when you get close to 90 degrees, it gets noisy. And part of that, there's a kind of a kink in the curve. And it really worries me, this transition that you described between beam width limited in sonified area and pulse length limited. And it's very sensitive. And you mentioned that just to that point, just as you were really wanting to work close to normal incidence, all of a sudden phase gave up on you and you were forced to abort and use simple geometry. And one of the things that I think we both remember is as you rotated the plate, it would be lovely if we only rolled it and didn't pitch it, but we were actually, it was often kiting in the current. And you mentioned that there was a long track phase angle, which you didn't use most of the time. Could you tell us about it? First of all, why didn't we use it most of the time? And could we have perhaps used it to try and get a better grazing angle at near normal incidence? So
yes, very good points that you made here. So first thing, when we don't have phase, any information for the phase, and we need to use just one ping. With the whole ping, we make a distract of it, but it's one ping, one information, one subset for each ping near normal incidence. Then we are smearing all the response near nadir we instead of having this high definition response that we have in lower grazing angle, near normal incidence, we just have one subset, one point that gives the information there. So that might be mirroring the response near nadir. But the other thing that we may need to reveal is the area, the instantified area, actually the instantaneous instantified area formula that I used just for the normal incidence. And I think I did not consider the slope that is not exactly straight 90 degrees, but we may have some cosine, some projection on the seafloor that we need to make it. Maybe it makes the smoother that slope that we have for the area. If I can go to the plot really quickly, which one's that? So it's just this one. So we can see this difference of slope. Maybe it's not shouldn't be that steep. Maybe it could be smoother if I have this formula corrected or better, more accurate. So that's another thing. And the other part that you mentioned here. So I'm trying to remember the other aspect of this that made a very important point here.
I think the other thing is that, well, what I'm actually leading to is the fact that you said, in principle, it doesn't matter what seafloor we're on.
Right. So
if you, as you're now suggesting, maybe we're smearing the grazing angle response near nadir, is if you had a choice to calibrate of all those 5 areas, which one would you find would actually work best and why?
So based on that aspect, that the near normal instance we are mirroring the response. So maybe this muddy sand would actually have an even higher specular response. It shouldn't be even greater near nadir. If you compare with the cobalt, which is a red smeared, then we shouldn't have any problem. So if I were to choose, if I had the options of this amount of sediment types available, then I would choose the cobalt here, since we wouldn't have the effect of the near normal incidence problems.
It's more of a comment that just actually 2 days ago, there was a presentation by Fugro that was showing angular response curves from a lower frequency than any of this. It was a 30 kilohertz system. And it was shocking how the specular peak was within 3 or 4 degrees of normal incidence. It would drop something like 7 dB. And I think this may be a little bit harder. Would you, just last before I'll pass it round again, if we wanted to do this for deep water systems, like 12 and 30 kilohertz, what do we have to do differently? Are there any, does this scale?
Well, the first thing you need a plate that is reasonable, can hold this transducer, that are wider and of course heavier. But I mean, we have more problems with the higher frequency when we had deeper. So when we are in the mud that had lower response. So here in the mud we have lower response, lower backscatter strength, and it is 55 meters. So we have a lot more noise here. So we have problems with higher frequency, and we wouldn't have these issues with lower frequency. So that's something that we wouldn't need to worry about for the lower frequency. But in logistics, we will need to build a plate that can hold these transducers, and how to manage that.
It is heavy, very heavy.
It's heavy, yeah.
Okay, I'll let our cycle round. If Brian, you want to have another?
Sure. I was just about to ask the question you just asked about which bottom type would you prefer. So I'll build on that a little bit. You just talked about if you could scale, if you could do it with deeper water systems and so on. And so what occurs to me is that yes, you can do it with one calibration but is it better if you had more than one? So the question is, how many calibration sites do you think you actually need? Do you just need one and everybody has to go there? Or do you need a group of them around the world? Or do you need a few in a certain spot? If we're going to do this, what would be your prediction for the best way to set this up practically, assuming that we're going to want to do this on every system before we go and start doing the NOMEC mapping?
Well, it is very important to select a suitable area. It's not, I'm not sure how easy it is to find places that are suitable along different coasts. Here near Canada, we had a lot of things that helped. So we had protected areas that we could anchor there, and we can see the ship that the vessel that we used it here, and the sea is very flat. We don't have any problems with currents most of the time. We don't have problems with navigation. We're not in the middle of a channel, so we can anchor there and do the procedures. And we have areas that are not subjected to turbidity currents or variable of the sediment type over the time, or producing some ripples. So we have flat areas. So we have flat seafloor in a wide enough area that can cover with the same sediment type. So that should be investigated before selecting the area, so we can use this procedure. So maybe you're not able to find several places. Then if you have one, maybe should be enough. I don't see any reason why we would need to have multiple sites. I think one site should be properly, if it is good enough, if it respects all this it's not requirements yet, but if you want to say those requirements for that area, it should be fine.
So you have a fairly clear idea on what's required for the area. So it's something you could very easily make a list of. Say you must have this. If you can meet all of those requirements, we can do a calibration here.
Yes. So yeah, I have a hidden slide that you might have seen, but if I think it's number, yeah. So I select some characteristics that would help us to select the area. The first one being flat, since we are using the grazing angle from the MRU some of the times. It should be smooth, so we don't have any ripples that would have variations from azimuth, so we don't have any azimuth dependency. It's important to be homogeneous, which means the same sediment type in the whole area. We don't want that to have both boulders and mud, so we need to have, we don't want a spike response in the angular response curve. So we want to build a corresponding angular response curve for that sediment type.
Sorry, carry on.
Yeah, it's interesting that the area is stationary, meaning we don't have changes of the sediment type a long time. But if it's not stationary, you just have to calibrate at the same time. We make the measurements with the split beam, and we make the measurements with the system that we want to calibrate at the same time. Then okay, but it won't help it any time further. It's just for that time. Having a high backscatter strength, so a low speckle near nadir, as we discussed it, would help getting rid of this, because we have a wide, the split beams are 5-7 degrees wide, the beam width. So near nadir, it's mirroring of the response. So if I have a higher response in the backscatter with low speckle, would help. And if we want to go as shallow as possible, so you don't have much noise, much interference from the target, so from the transmission loss. And if you can drop the equipment closer to the seafloor, you don't need to have the equipment closer to the surface. If you have enough equipment to go deeper, closer, decreasing the elevation, then it solves this issue. And in this case that we were anchored, it should look for areas that are allowed for anchorage.
Okay, so it sounds like from what you're saying and from what's in your thesis that the setup for this is quite elaborate. You need quite a lot of work to put together a calibration spot. So that makes it problematic for everybody to do it. It's something that you need to have some specialists to do from what you're saying. So if we want to calibrate every system that goes out, do you think, so two questions. First one is, do you think that the average survey ship could do the calibration? Do they have the right people on board? I mean, is it possible to do that? Can you imagine that happening? And the second one is, what's the level of effort involved for a ship to calibrate, given that the calibration site has already been set up?
So, well, I think it is an important question that I have to ask myself in Brazilian Navy as well. Mm-hmm. So we have, at first, we don't have all the equipment at first hand. So we would need to have these split beams, these four transducers in that case. So acquiring that is not cheap for a company that has just one ship. It's for a greater institution. But let's say we are in the Navy and we can provide that, or we can rent or make somehow it's cheaper, and we can produce and we select an area that is at least a little stationary with time. Then we can provide. Maybe we could provide the reference and other ships from different companies that can get for the Navy, for the government, this reference that could calibrate their systems. So it's more making broader. Yeah.
So this is an ask for the hydrographic organizations. You know, we want you to go out and collect data, so we're going to provide you a calibration site.
I think that's a good way to go. Other way would be maybe the companies, like manufacturers, can provide that as well. Mm-hmm. Maybe they can provide a service for that if the market shows interest and really appreciates the effort of calibrating that. Mm-hmm. And I think it might be reasonable.
Okay, all right. So that's interesting. That's one more thing we need to go ask. That's okay. All right, I'll pass the questioning on to Tom.
Okay. First, I'll make a comment since it's irresistible to me, and that is that you made the point that you really only need one calibration site, and there's a great, I think, saying that's probably attributed to Mark Twain that says, "A man with one watch knows what time it is, and a man with two is never sure." So it's certainly safer to just use one, because then no one can argue with you about how accurate your calibration is. I have another question to follow up on John's question about, what would it take to go do this, for a deep water system where, you got to, now we're talking about a seabed that may be 600 or 700 meters deep or something like that, however far it takes to get out of the near field for a half degree, system at 30 or 12 kilohertz. And that question really is, do you have to do this on a pole suspended, on a plate suspended on the side? Could you, I'm just thinking back to, some of the stuff that Carlo Lanzoni and Paula Boy have built for us for other calibration techniques where they were putting EK 60 transducers, in that case, that's when it was, on a very nice rotator mounted on a pole on the side of the boat. And they're just rotating through, in that case, not looking at the seabed, but in your case, it could be looking at the seabed. Would that work? Could you do that? I
think that would help if you have a way to mechanically rotate without using ropes and being on the board of the ship, yes, that would be great. And maybe it could go. And if actually, if you want to deploy the equipment to get closer to, maybe you don't have areas that is that shallow that we had here. Maybe the area that you selected is 100 meters deep. Then you probably need to deploy the equipment, and you would need this mechanically rotated motor or mechanism that doesn't need ropes or a person near the edge of the ship.
Yeah, or we're just going to have to call you up and have you. We don't all have Ivan-sized grad students, so we'll have to come, find giant grad students to do this. Okay, but if there's not a fundamental limitation other than, I get that maybe there's an extinction range at some point for the very high frequencies, but 30 or 12 kilohertz at in 700, 800, 900, 1,000 meters is probably just fine, I would think. But that's okay. That's good to hear. Can we go to slide 37? I just had some questions about. Oh, maybe I have a different slide 37. Oh, yeah, that's it. I just was interested in looking at some of your actual data results. And one of the things that struck me is really came through on this slide, and that is that on the model on the left, you see that lovely looking bump out near the critical angle that we always put in our models and always make a point of pointing out. Did you ever see anything like that in your data? I think you're looking out to grazing angles that should include the critical angle for sand, maybe, although I guess you don't really know what the sound speed is. Did you ever see any evidence of that critical angle bump?
I did not, actually.
Interesting. I don't know that means anything. I was just curious whether we actually observe it. It'd be a really useful thing to observe, because then that starts to provide you a sound speed for the seabed. There's another one. I don't know. It's your frequency response slide. I'm not sure which one that is. I have your slides here someplace. Maybe slide 42. So you have some interesting results here, and they somewhat contrast. Well, there's a couple things that struck me, and that is, I think you probably have maybe some calibration things that might change these curves a little bit, get rid of some of that ripple, and that maybe might arguably even flatten some of those curves more, but they're flat anyway within a couple of dB or even less. And is that what you expected based on what's been previously reported in the literature for gravel, sands, and muds? You actually have it flat for gravels and sands and decreasing for mud, if we ignore the very highest frequencies for mud, where I think you were saying you were having SNR problems. Is that what you would have predicted?
Well, to be honest, Thomas, I didn't make the actual comparison between what we had in the literature with this specific response. Yeah.
There's some really nice sort of compilations of these kind of data in Jackson and Richardson's book that would be worth looking at. For the other thing that really, so you should get a big pat on the back for, is that you're now operating over a decade of frequency, and that's pretty impressive just by itself. So nice work there. The thing that is interesting to me is that when you look over a decade of frequency for sand, it typically increases with frequency by 7 or 8 dB. The cobble, or maybe, I'm not sure about gravels. Cobble, which you don't have on here, or maybe that's what you mean by gravel?
Yes, we have shell hash and cobbles here.
Yeah, okay. Those are maybe smaller, but still increasing a bit, maybe a few dB. And then muds, I think, are flat. Why do you think your muds are, what would cause your mud to decrease, not even over a decade, but over half a decade, from -20, that's decreasing by 10 or 15 dB? That's a pretty substantial one. Any idea what's causing that? What's the mechanism there?
Well, no, the honest answer is no. I have no idea why it is decreasing, but and then we have it is decreasing with 75 degrees and 35 degrees, and actually if you want to take a look at each of one of the grazing angles that we selected, or not selected here, but we had in the data, it is constantly decreasing. But that's all that I could infer from it.
Yeah. The other thing that strikes me about this is that if you're sands and gravels, 200 kilohertz, 300 kilohertz, 400 kilohertz, you should be seeing the same thing. That's what your results are suggesting. I don't know how widely applicable that is, but it's an interesting result for sure. Okay, I'll pass on. Pass it along.
Yeah, no, it's a conversation, I think, well beyond this thesis is, the applicability of these results. I'd make the comment to Tom, that decrease with frequency, I think that's sub-bottom responses, and that was actually a mistake that was, well, in hindsight, everything's a mistake. The area was chosen because at 300 kilohertz, it was homogeneous. When we finally went in there with an EM710, it was quite a bit of variability that suggests there was buried scattering. So maybe it wasn't the best mud.
Yeah.
But of course, obviously, if there is something, it's subsurface. As you drop frequency, it appears. But yeah, these are fascinating results, and you want to hand it over to a modeler now. Mm-hmm. The question I would have actually, Ivan, is we chose to anchor spin around. It was partly because it was easier to do. But I look at the two other works that you quote, what Tom and Larry Ward did is they averaged over a transect, the Nubex line. And so there's kind of a bit of a spatial averaging there that might be more stable. And then you look at Ifremer, they pick an area, but they did this star pattern. So again, they ended up averaging over 500 meters. And as you point out, the low grazing angle really is spread out because you do all the azimuths. But at normal incidence, most of our observations are within probably a 10-meter radius circle. Have you thought at all about whether it would be better to be anchored or underway or drifting a little bit? Should we be averaging a little bit?
So, well, there are some benefits from being anchored. That the first thing, you don't have the pressure of the water unless there is strong currents. But if assuming you are drifting with the water or there is no current at all, then we have your plate just tilting by the pressure that you put on your ropes in this case. So you don't have to deal with this pressure in the water or horizontally. Whereas if you are on underway with the ship, we would have this problem. And that's one thing. But the other thing that once you are concentrated at one point, and the area that you need to cover with the same type of seafloor, with same type of sediment, the area is narrower. So you don't need the requirement of an area that is along the whole way the same type of seafloor.
Okay. Yeah. I mean, as a marine geologist I once was, there's when you get down to most seafloors, they always are heterogeneous if you get close enough. But this is something I think we have to consider, and I'm struck by Brian's question, or maybe it was Tom's, that should we have multiple sites? I kind of wonder if you had one of them, we risk it not being stationary for whatever reason, something burrows or the currents arrive. If you have 3 or 4 sites under different environments, if one of them becomes unstationary, that's a word, then you would be able to compare. It's like luring 3 to 4 sound speed probes. If one of them doesn't match the other, suggests a different calibration. So I think this is, well, do you have a comment that if we're going to establish, well, outside Rio, you know, for the Brazilian Navy, should there be one site, or would you recommend a bunch of sites for calibration of the Brazilian Navy's hydrographic fleet?
I think it is another beneficial thing of having multiple sites, but you just need to use one. If you're going northway, you just go to that site, do your calibration, and keep with your mission. And if the mission is to the south, then we go to another site that is towards south. Then you don't have to go around and lose that time, invest that time. So it's beneficial if you have sites closer to the area that you are going to survey. So it's not a problem having multiple sites.
Yeah. You almost want a national program that walks through all the sites regularly to confirm they remain the same answer, potentially, whether that's a government requirement.
Yeah, you can calibrate with your system at one site and go to the other site and check if that calibration was good enough to get the same results on the other side. And that's the question of having 2 watches, but it's beneficial to have that out and see how accurate you are with your measurements. And the other thing is, in Brazil, we have the coastline just as large as the US. So we cannot have one ship going to the north of Brazil to go to the other side, to south, to do the survey. So we would need a calibration site at north for those ships that are seated there, and another on the south, another in Rio, another in Salvador. So we would have sites along the coast and in the rivers, if you wish.
Well, I think I'm quite happy. I think there's a few Q&As in there. I don't know whether I should open up or Will. Do you want to look at the Q&As if you're there?
Hey, John, I'm happy to jump in and throw a few of those out there. And in fact, our Ivan fellow student Liz had a question which she said she'd be happy to ask live. So Liz, if you'd like, I can unmute your mic and you can ask him instead of having us read the question. So I clicked allowed to talk. So if you want to jump in, go for it.
Can you hear me?
Yes.
Excellent. Ivan, congratulations. That was a great presentation and nice job getting everything done in a tough time. I feel like during the committee questioning, you guys kind of danced around the answer to my question, but I was wondering, your ground truth sites, especially those with the cobbles, the gravel, the shell hash, I imagine in a natural environment, there'd be quite a lot of heterogeneity in terms of the distribution of those sort of large, cobbles or shells that are sitting on the sea surface. And when you did your calibration with your EK systems, is there any way to account for sort of the uncertainty you might have that stems from surface heterogeneity? I mean, obviously, I think quantifying that might be difficult, but did you discuss that in your thesis, especially at the higher grazing angles and the higher frequencies? I imagine you would see quite a lot of variability across the region.
Well, thank you, Liz. Liz was very helpful with my project, actually. It's helping me a lot with the codes and the calibration part of it. She's an expert. And thank you very much for your question. So we have found on pictures of the C4 had a camera, not only we had also ground truth, but we've had a camera that showed some boulders near the cobbles areas, and that made some variability on the angular response curves for those sites. And the way to I think the best way to get around these is making as multiple collection of data as possible. So we tilted the plate several times, collected a number of data, and that makes these spikes less important, if you wish. But still, I didn't have a method to quantify how it impacts the results. If that's, I don't have that on my thesis. That might be very interesting to get at this point, but I don't. In my thesis, I just have the method here to build the reference, actually.
Great, thank you. I imagine sort of an ensemble average would help you sort of remove spikes that you might see from some kind of very large boulder in your field. I was just wondering if there was a discussion of that. I imagine that, I know you guys were talking about a single site that multiple ships might come to, and obviously in the natural environment, those types of sites might change. And you mentioned that, you said, we want something that's homogeneous and stationary. So it might just be a matter of observing occasionally, like with a camera, what you're looking at. But thank you, it's great.
Thank you.
Okay, thanks, Liz. We have a couple other questions from the audience, and hang on, let me cue those up here. And so I have one from Pedro Teixeira, who says, "Great work, Ivan. Based on your experience and results, which EK frequency band, if any, would you say is the most informative about bottom type?"
Oh, I was reading with you, but it's,
oh, excellent.
So which EK frequency band would you say it's the most informative of bottom type? Well, I would say it depends, and we can see that depending on the type of seafloor, you can make them different apart by selecting the proper bandwidth. And maybe if we have enough information from different seabed types a long time, we can build a library that we can make those comparisons and actually select, oh, that's the best. So I want to know if it is a sand or a muddy sand, or a cobbles or a gravels, then I will select the proper bandwidth transducer to then identify that. And I think that's interesting if a long time we build this library with absolute response here. So this reference should be honestly the response for any other site that has the same type of seafloor.
Great, thank you. We have another question. Oh, I'm sorry, go ahead.
Ivan, is part of the answer right on the slide that you have up right now? Whoops, not anymore. Yeah. If you're trying to discriminate between different seabeds, are you just looking for the largest spread in the data?
Well, but I wouldn't say that, because if you look at the other axis on the angular response curve, we can have, you can differentiate them more than just these. This is the difference between them at 75 degrees. And if you take a look at 35 degrees, you can see that they are further apart. So if you take a look at the angular response curve, then I think it's just more beneficial to select the bandwidth that you want. If you go back here, on those examples here. So if you want to differentiate cobbles and shell hash, I would pick the 51 kilohertz because they are at this frequency, the responses are further apart. But if I want to differentiate to muddy sand, I would pick 200 kilohertz because the angular response curves of each one of them are really different characteristically. I think it's by looking at those information, it's more beneficial to pick the best bandwidth if you have all of them available first.
Right. Okay. Thanks.
All right, Ivan, we have another question from another fellow student. Clinton Marcus asked, Ivan, congratulations on a great presentation and on completing your work. My question is this: can the methods you prescribe for calibrating an MBES system be translated into calibration methods for other such systems as LiDAR or satellite bathymetry?
Well, if they work with the same bandwidth, I would say yes. But let's say LiDAR, it is, well, I wouldn't say LiDAR is the same because it is, we are telling about electromagnetic, it's not acoustic waves. So the response, these responses are acoustic. I wouldn't say that for the LiDAR would have the same intensity response. So I wouldn't say that for LiDAR is the same. And for satellite bathymetry, and I believe it is about the altimetry of the variation of the gravitational potential there. So I don't believe there is any intensity involved in this. It's just the variation that makes the bathymetry there. So I don't believe that for LiDAR and for the satellite bathymetry, this method would apply. And maybe for LiDAR, we could develop a similar method, but using calibrated LiDAR systems instead of the split beam systems.
Okay, thanks. I don't know if maybe this might have been answered or not, but I figure it's the last question in the queue. So it's short, but David Faber asks, Ivan, did you do any windowing like cosine tapering for edge effects before the FFT?
Well, other than the windowing that the transmitted signal has in its ideal construction, I didn't do any other. So when I selected the size of the FFT as 64 samples, I just cut that and I used that. I could have used a cosine tapering for that to avoid the edges. I did not, and we saw that at the edges we have these higher spikes. But maybe this cosine tapering wouldn't solve actually that. We just get rid of this information on the edges of the transducers, of the frequency range of each one of the transducers. But for building the transmitted signal that you use for the match filter, then yes, we use the windowing and the filter that is used to build the transmitted signal of the transducers. Yes.
Great, thank you. And looks like we are, John, I want to hand it back to you. I think we're out of questions at the moment. And I didn't know if you wanted to proceed any further with additional comments or questions. And I know that at some point the advisors committee will make their way into a private session discussion with Ivan. So
I think just, sorry, Will, I think it just popped up another question here.
Oh.
Yeah. Do you want to answer that, Ivan? You can read it or read it out to us first, but I think that'll be the last one. Yeah.
Yeah. So yeah, this is an important point here. For the area formula stated are for flat seafloor surface. If I'll just bring the area before, and then I can read it. Let me find out where it is. Okay, 34. It's slide 34. So the question is about the formula, and for the area formula stated are for flat seafloor surface. Is the area worked on are all flat? Okay, someone changed it here. What is that?
Oh, it's in answered. Or...
answered, or the?
Is the seafloor slope included in your?
Yeah. So yeah, the question is the seafloor slope included on my project? It is not. I assume it's a flat seafloor, but it should. We should include that here. When we rotate the plate, we should use this cosine. So yes, there is some room for improvement here with this more accurate term for the slope of the seafloor, for sure. Yes.
I think, Ivan, you actually do when you're doing the phase, because you're getting the local grazing angle, which actually it gives you the across track slope, just not a long track.
Yeah.
But not at normal incidence.
Yes. The grazing angle calculated here is from the normal, it's between the normal incidence of the seafloor and the ray. That's fine.
Okay, I think at this point it's been a long session, and I very much appreciate that, Ivan. I know it's very hard to do when we're all on multiple sides of the planet, but I think a round of applause, even if you can't hear everybody's applause. Thank you very much, Ivan.